Hello, namaste everyone. It's our sixth webinar on microgrid energy from inside out, organized by Electrical Engineers Welfare Association, Nepal. I am Vinod Sharma, the Executive Secretary of this association. On this auspicious occasion, I would like to welcome the President of Electrical Engineers Welfare Association, Nepal, Mr. Rajendra Dhakal, and other executive of this association. I would also like to greet and welcome today's chief guest and the speaker of this session, Professor Dr. Josep M. Guerrero from Aalborg University, Denmark. I also like to welcome. I would like to welcome all the professor, associates, heads, and directors from different organizations, universities, and departments. Also, researchers and students from many universities who are with us today. I also like to welcome all the viewers on our Facebook Live. First of all, we are thankful to Nepal Research and Education Network, NREN, and Nirajan sir for hosting webinars for us. And today, we are very honored and thankful to our guest speaker, Professor Dr. Josep Guerrero, for sparing valuable time for us from his busy schedule. It was like a dream event, and I'm glad it is happening today. So I personally, from the side of association, really appreciate your professor. Now I want to introduce our speaker with his short biography, though many of us already know him. Josep M. Guerrero received BS degree in telecommunication engineering and MS degree in electronics engineering and the PhD degree in power electronics from Technical University of Catalonia, Barcelona in 1997, 2000 and 2003 respectively. Since 2011, he has been a full professor with the Department of Energy Technology, Aalborg University, Denmark, where he is responsible for the Microgrid Research Program. He is a founder and director of Center for Research on Microgrids, CROM. He is also working as a guest professor for many renowned universities from different countries. His research interest is oriented to different microgrid aspects, including power electronics, distributed energy storage system, partial and cooperative control, energy management system, and optimization of microgrid and blended microgrids. Professor Guerrero is an associate editor for a number of IEEE transactions. He has published more than 600 journal papers in the field of microgrid and renewable energy system, which are cited more than 53,000 times. And Josep M. Guerrero is very popular name in the field of microgrid, with H index of 102 and I-10 index of 570. He received the best paper award of the IEEE transaction on energy conversion for the period 2014 to 15, and the best paper prize of IEEE PES in 2015. As well, he received the best paper award of the Journal of Power Electronics in 2016. During 6 consecutive years, 2014 to 19, he was awarded as highly cited researcher with 50 highly cited papers. In 2015, he was elevated as IEEE Fellow for his contribution on distributed power system and microgrid. It's just a summary of his work. It will take me more minutes to describe his complete work. Now, we'll move directly toward the awaited presentation. There will be few time for question answer at the end of presentation. You can message us your question. We'll take as many as possible. Now, without consuming more time, I would like to request Professor Guerrero to start his presentation.
Yeah. Thank you very much for your presentation, Professor Vinod. And thanks very much for the organization to give me the opportunity to go to Nepal, let's say electronically, which is the first time that I visit this country. Yeah, and I also appreciate very much the hospitality, and we have also inside our department also another person which is also from Nepal. So I know very well your hospitality, and we really appreciate it. Well, I'm going to give I also want to give the thanks to many people that I can see here in this community that today is connected, and many friends, good friends, and also members from our Center for Research of Microgrids in Denmark, and from many other places in the world. So thanks to all of you to be here. and I hope that it will not be very bored for you. For me, more important is it's to present a little bit some ideas and concepts, and then we can go for the questions, which is going to be maybe more interesting, because it will be what you are more focusing and what is the problems we want to solve. No? Okay, another thing is that you can also send me an email anytime. You have here my email. You can also do it through Vinod, and here is also the website of our center. So if you need more information, you can also access in, and if you need something else, just don't hesitate to contact us. Finally, I would also like to thank the Velux Foundations to fund part of our research during these years, and of course our Department of Energy Technology and the university. Well, this is a little bit about me. So you can see here, Vinod already present a little bit of my CV, but I would like to say that more important for me, it's like from 10 years old, I was very curious about electronics, and I entered inside all the things, especially telecom. Telecom is something that always has been driven me. This is a very important thing. And I will say that right now, even we have a very nice world ongoing with telecom. I am one of the ones who escaped from the telecom world, let's say, but now because energy is also coming with a lot of telecom challenges, it's like coming back home. And the other important thing for me is also music. So I normally play a lot of electric instruments. So the electricity is also very much connected, no? Even today we have electric drums, and I think that this is something that is changing, no? I'm also very happy to have been developed real products that right now are in the market, like those that are here. And this is something that is also important to see when we want to make research, try to have some impact, no, in this world. Another important thing, we have very nice and important targets. For instance, Denmark already, as a country, said that wants to go on. Denmark, as a country, said that we already want to target 2000 in 2015, 100 renewables. We are right now almost in the 60%. More than 50% of electricity last year was coming from renewables, basically wind turbines, and we are almost right now in the 60, let's say. So at the same time that we have these ambitious targets, we have still in the world 2.7 billion people without access to electricity. And this is really a problem. And this is what we have to face. All the other, I think it's nice, we have to do it, but that's an important target. Yes, and I was also presenting a little bit about our Center for Research on Microgrids. We have several use cases in which we make research and development, rural areas, industrial areas, also electric ships, also electricity, more electricity for the space and satellite systems. This is a picture from our team also. Hello guys, I know that a lot of you are also connected. And here we have some part of the team. We have a number of postdocs here and assistant professors working with us, and at the same time, a number of PhD students. So you can see here some of the topics. But if you want to know more, you can enter in the website. This is a little bit more about our, let's say, facilities. So we have, let's say, some facilities to make tests on different microgrid aspects. Including also marine things. This is our traditional DC laboratory also. And then we have also facilities, real facilities to test, let's say, in an environment of a house. We erected a small wind turbine of around 5 kilowatts, and then we put some solar panels in the roofs. So those facility systems, you can see that we have also the flexibility of integrating different appliances and the generation part. No, I know that a lot of people working on microgrids are very focused on the generation part, but if we are not able to reduce or to save energy from let's say from the consumption part, it's going to be very difficult to do something, because we have to also bear in mind that it's not common that you could have solar panels in your roof, and even less common to have, let's say, wind turbines like here close to your building. So that's why we have to focus more and more on those appliances. Then those are more nice pictures from our university. So in the front you can see the building that are of offices. And then here is our demo house, and then behind that you can see also the laboratory buildings. Yeah, it was a sunny day, like those days, very different than during the winter. Now you can see here how is this demo house that we have. It's like this is the main entrance, and then you can enter through the. You have here the control room in which we have all the telecom devices. And then we have the area of the kitchen, living room, and office. Yeah. So you can see here some of the pictures here. We have the living room. It's very nice also to have a nap, for instance, after the lunch. And we have here some office space. All those occupied space, we have temperature sensors, light sensors, and so on. Yeah. So for as office, it's fine. As a house, let's say we have some difficulties of our available structure, as I showed before. Yeah, we were just having the nap here in the sofa. Yeah, and you can see here a little bit more of our, let's say, control room and the kitchen as well. And here is a little bit the deployment of the smart meters. So this is just a smart meter, together with what we call also the prosumer meter, which is measuring the wind turbine generation. And then we enter here, we just subtract one from the other, so we know exactly how many power is coming from the wind turbine, and how much power we are injecting or absorbing to the grid, because right now we have like bidirectional smart meters. Yeah. That's also something very interesting. We just plug some, let's say, what we call smart plugs. Those plugs, it looks, let's say, very normal, but inside we have a microcontroller using Zigbee communication systems. And you can just monitor, let's say, voltage, currents, frequencies, and so forth. All this information is back to our central controller, so we can know exactly, let's say, the electric characteristics of each of the appliances we connected, and then we can connect or disconnect also them through a switch. There's a switch connected, let's say, through communications, but also we have a manual switch. In blue, this is a little bit special. This is a DC distribution plug. It's made by Fujitsu. Yeah, but unfortunately, as you can imagine, it's not very successful for home applications, because basically almost there's no DC home in the world, in the real world, let's say. And this is another picture from our lab. We are also able to, let's say, from MATLAB Simulink codes, compile controllers and to test with real devices, let's say. And then you can see here also from, let's say, from the demo house, we have also a gateway. And from this gateway, we are able to link different devices using Zigbee communication, Z-Ways, wireless, and so forth. So I will say that that's a very powerful one. Those are the different devices that we can also integrate, and we already did. And this is a little bit about the platform, which is based on an IoT architecture. We are part of this fireware, and then you can see here about the database systems that we use, the broker, and all the connections with the different agents. Yeah. And this is regarding the load priority. So we are able to connect different, let's say, electric devices here. And then if we surpass certain amount of power, we are just able to disconnect and to give more priority to others. Please don't touch my presentation. All right. Another thing that we do is we are also able to make load monitoring, and this is thanks to using what we call also non-intrusive load monitoring. In the house, as you have seen, we are using plugs, which are, let's say, a kind of a intrusive load monitoring, because we have to add these additional plugs. But we know that in many houses, this is not possible. So then what we have to do is to disaggregate in a process in which we can just looking at which is the information that we have from the smart meter, what is the part that belongs, for instance, to an electric heater, what part belongs to a microwave, and what parts belong to a fridge. So we are able to disaggregate it and to know exactly which are the devices that we have here. Yes, and here you can see as well the different, let's say, waveforms. So basically a microwave, a dishwashing machine, and a coffee maker. Yeah. Is it going well with the slides? Because I can see that, Sandeep, yes, you are making some changes.
Yes, sir.
All right. So then, of course, what we need is here we develop different kind of, let's say, artificial intelligence algorithms. And we did it, and it works very well. We have very promising results in this area. Yes, and we talk about artificial intelligence, but still sometimes I'm not clear if we know about how our brain works. Yeah. Well, the people, let's say, major part of us, we think that we have one brain, but indeed it has been demonstrated by neuroscience that we have 3 points in our body with a lot of neurons. One is in the mind, the other is in the heart, and the other is in the gut. What we say, it's all this digestive part. And we talk about 1 billion neurons in the mind, 40,000 neurons in the heart, and then all the digestion system, we are talking about 100 till 500 million neurons. So, and this is very well connected, let's say, with the chakras from different, for instance, from India. And you can see also the connection, let's say, with the dorsal spine. So this dorsal spine, if you take a look on this dorsal spine and the connection also with all these centers of neurons, it really coincides with these chakras. So that's something very nice. And also right now many centers like Health Math Institute in Germany, they are also studying what they call heart coherence, which means that your waves from the brain can be also coherent with the heart. And once you reach this heart coherence, it's more difficult, for instance, that you enter in a heart attack. Sometimes it happens that the heart goes in certain vibration, maybe out of phase of what we have in the brain, and then it can cause, for instance, heart attacks and many other diseases. So this is, of course, this can be, of course, improved with meditation and many other things. Right now, even we have devices, some wearables that also are IoT connected, that allows you also to make a better meditation. And it has been also measured right now by neuroscience that people who normally practice meditation, they improve all this heart coherence. The other important thing is that, yes, we talk a lot about electronics, but we really know how the electrons work. And this is something that we are talking about many, let's say, years ago, even almost century. So we talk about a lot about electronics, but really we don't know how the electrons work. And when you go to the classic physics, they said that the electron was like orbiting with the, let's say, with these protons and neutrons, the center, let's say, the nucleus. Yeah, it was like a solar system, let's say. But of course, this was this theory was totally destroyed after the first experiments of Bohr. So these Danish scientists already saw that something was wrong. And then after this, a lot of, let's say, quantum mechanism starts to appear. So basically, if you think about the nucleus, it's almost nothing. If you imagine, I always put the example with London. If you imagine the London city, and you put in the middle a soccer ball, the soccer ball will be the nucleus, and the whole London will be like the whole atom. So you can imagine that when we talk about mass, it's almost no mass. And the electron, there is no way we can find it. We just have probabilities to find the electron. It don't have any orbit. Indeed, it has been demonstrated that the electron can be in any time or in any place or in no place at the same time. So that is what happened exactly with this kind of particles. Also talking about what is inside the electrons, what is inside these protons and neutrons. We talk about quarks, and those kind of quarks, they behave totally different that happen in the in our big wall. Things like time or space make no sense. So one of the first discoveries, it was at the beginning of last century, was the entanglement. And the entanglement means that we have two, let's say, two quantum particles, and they have, for instance, they are close to each other and they are synchronized. Once they are synchronized, also their spins are synchronized. So basically one spin will be always the opposite than the other. Once we put, it doesn't matter the distance. Automatically, once we see the spin of one, the other will have the opposite spin. It has been mathematically demonstrated, and right now we also have the experiments that demonstrate that. Recently, a Chinese satellite also put two particles on entanglement between the satellite one and the other one who was on the Earth. This is something that didn't like very much Albert Einstein, so he called something like the phantom effect, and he was always against that. Today we can see that some people start to say that maybe this is because of synchronization of the whole matter in the universe, and then we don't talk about entanglement but about super determinism. So that means that it goes on the other way around. The other important thing is about reality. So we let's say that if you take a look on Platon, for instance, who was a Greek philosopher, he said that the reality was like if some people are inside a cavern, and then someone, and these guys just see the caverns and some shadows, and the shadow, it comes, of course, from the light that is outside it, and they were thinking that those shadows are the reality. So somehow, let's say, Greek philosophers already knew that reality is something that is more created inside you than something that is outside you, right? So also, it's kind of the same that what we can see that when we try to observe how one of these particles, like electrons, behave, if we don't observe them, we can see that they behave like waves. But when we try to observe where this electron is going, then this waveform just collapses, becomes like, let's say, a mass. It's a particle, so it's not a wave anymore, and then it just go from one of these two holes. This was a very old experiment, and it's very interesting because this means that when you are observing something, you are affecting the reality. This again didn't like very much to Albert Einstein, and he said something like, I would like to think that the moon is there even if I don't look at it. Yes, but this is something that we have been demonstrated, and it's right now very well known that in the quantum physics, this is basically not true. So it depends on how this works. Another thing is that teleportation. Yes, we know that it comes from very old science fiction movies like Star Trek, in which, for instance, one astronaut can be transported from one place to the other. And you will say this is impossible, but nowadays, we are able to do this with photons. So some experiments are carried out around the world. For instance, in the Canary Island, with some kilometers, they just destroy one photon, and the photon, they can transport it to another place. The scary thing is that, of course, the photon that goes from one place to the other has to be destroyed from the original place and recreated in the new place. Yeah. Right now, it's only done with photons, and it's already, well, very well known, and right now there's a lot of, let's say, experiments ongoing with that. So things that we thought that are basically impossible are starting to be possible in the quantum physics world. So finally, also, it seems that let's say, the reality creation is some process that goes from inside out. It has been demonstrated also that many things that we have today that in the past we thought that it was basically impossible, they start to exist in movies. So somehow from the, let's say, from our subconscious, we start to create this, and then humanity start working to make this possible, right? So it's part of this reality creation from inside out. And when we think about also that energy and information is over this duality of matter and wave, we believe, why not also changing the energy paradigm as an inside-out creation, right? So this is also what our, let's say, microgrid paradigm wants to do. It's very important that if you analyze what means paradigm, it means it comes from two words. One is para, like parallel, and the other dime is like a dogma, so something that you believe on. So it's very difficult, of course, to change paradigms because they are connected with your beliefs. So it's very important, if you want to come with new paradigms, to change your beliefs. And believe me that this is the more hardest task you can do. The other thing is, like, when we try to define a microgrid, I will say that a microgrid is just a grid. It's nothing else like a grid system. So you can imagine it can be electric, of course, can be thermal, can be both, can be energy systems. So even can be water. Yeah. So whatever you want to transform and you want to process. So what the, let's say, the microgrid paradigm change from, let's say, the classical one. The change here is that when we think about big power systems, we have just some energy that comes to our houses, and then we just pay a bill, and then because we pay this bill, the user have the right to use it, right? So there is like this association on the customer point of view from where this energy, electricity, or whatever it comes, it happened also with the water, from where it comes, to what sense it makes sense to take care of that, and so forth. So there is a lack of awareness on that. When we think about a microgrid, there is a raise of awareness, because basically the microgrid tries to generate consume and storage the energy very close to the point in which you will consume finally. So it's just proximity, what comes with the definition. And the other important thing is sustainable, but not sustainable in a political way, sustainable from the point of view of we have some resources that are available here, I can use it, I can install it, and then I am very conscient about that. So for instance, if I install some solar panels in the roof, I'm conscient that at noon, I will be able to use more electricity. Yeah, and I can tell you that as a user, this is what happens. You tend to connect more things. For instance, washing machine. No, you see that the sun is shining. You run to your washing machine, connected, and so on. And then you start to have more and more electric devices, let's say, in your place, because it's something that you are generating and you want to consume also. Yeah. So that's something very nice. The other thing is, like, there's a lot of nominations that has been raised in the last years, like talking about, because micro, it's like, yeah, it's like a unit. Then you can think about nano, pico, and so on to make it smaller, smaller, smaller. It has arrived to a nonsense, let's say, because we have no way to measure it. So a microgrid can be defined in the terms of megawatts or kilowatts, or could be even in the level of gigawatt if you think about a country. So that's very difficult to define in terms of power, and that's why has been appear all these, let's say, new terms. Yeah. But another interesting term that I will say that is less explored is when we say mini grids. So the idea of mini grids, it also, I will say that also comes together with microgrids, but you can see that in a lot of, let's say, places in which there is no electricity, like some sub-Saharan countries and many other places in which electricity, it's not present, and you want to build the electricity from scratch, then the mini-grid concept appears. But I will say that is exactly the same. It just, you can see some organizations like the United Nations and some others are using this term just for historical reasons. Yeah, I'm saying this because it's really a mess when you try to unify all these terms and so on. Another interesting thing is about what we are going to use, AC or DC. I think there's a very interesting movie that I will recommend you to see, which is called Current War. I think this film has been made like 3 or 4 years ago, so you can still find it. And you can see the life of Edison and Nikola Tesla and how they fight with this AC and DC thing. I think it's not only interesting because of the electricity part, but also about, let's say, these kind of personalities and so on. Yeah. Today I'm not going to explain those things, but you have to understand that when we think that we work in survival, like trying to demonstrate that what we want to present, like saying in the case of AC or DC, we are right, we have the right, then a lot of interesting processes are happening in the brain. So we have some part in the center of the brain, which is becoming bigger and bigger. And then when this part is becoming bigger, then you go more to the survival, let's say. And well, all the processes that goes in this direction, you can see it well described in that movie. So coming back a little bit, why it didn't make sense at that time to go, let's say, on DC? It was because they wanted to implement, let's say, electricity in big cities in the United States. And then if you work on DC, it was no way you can increase the voltage and you can distribute it along the cities without having a lot of losses, while AC you could use, let's say, transformers. So you can see this is a statement from Nikola Tesla to Edison. It says direct current may be fine for cities when the buildings are close together, but most of your country, meaning United States, because he was coming from Serbia, are empty spaces. Only high voltage can span the distance. You are not thinking long term, yes? And somehow was true, and that's why all the system becomes AC. At the same time, what happened, it's like when we try to connect our, let's say, solar inverters, in the case of photovoltaics, we need, of course, this AC to DC, DC to AC conversion. So it's basically an inverter. So to have this conversion, we have right now in the market several products, like those who work grid connected or those who work islanded. But I will say that right now there's the possibility of interconnecting those two, let's say, species together. And in yellow, you can see those connected maybe to battery systems who try to fix voltage and frequency inside your microgrid system. And in red are those who are just injecting all the power that they can. If you think that, for instance, your battery starts to increase a lot the state of charge, then naturally this system will go to a collapse when you have a lot of power coming from the solar PV, and then your batteries cannot absorb more. So how is the way that they work? It's kind of easy. They just, once the battery reach very high levels of a state of charge, the frequency in the system starts to increase. And then all this in red, they just decrease the power when they see that the frequency is increasing too much. Yeah. So this is very good because this is, let's say, compatible with the big power system, because you can see in the big power system, when we have a lot of power generation, frequency will increase naturally because we have synchronous generators that behave like that. But in the case of a microgrid, we can enforce this behavior just by changing the frequency of your microgrid system when the state of charge of the battery exceeds, for instance, more than 90%. Yeah, so that's kind of nice and cool, and let's say plug and play when you think to also integrate this into the big grid, no? Because also sometimes we, for instance, build a microgrid system, and we have to also think how we are going to also be compatible with the main grid. Yeah, and I will say that this is kind of very flexible to be connected. And the other thing, it's like, yes, there are some microgrids that have connection interfaces to the grid, and this is basically because if you see that there's a fault, you could disconnect the main grid and go to island. Yeah, this was something not possible some years ago, but I will say that a lot of companies like Fronius, SMA, and many others are already implementing this inside their catalog. So I think it's very good because let's say that the research stage of this has been finished, and right now we can see the first products in the market, yeah, which demonstrate also the mature of that, right? Also, some other companies like ABB has been promote also microgrids, and consortiums like those in United States, because you have to imagine that in United States they have a lot of blackouts. It's really a mess, the grid, so they need also to have microgrids. It's kind of less than we can see here in Europe, which are barely non-existent. In other continents, you can see that they need, for instance, in many islands. So we can see many islands, not only, let's say, in Asia, Pacific, and so on, that of course they need the microgrid. So we have to think that the microgrid is not, the market of the microgrid is not such big as some people say. but I will say that it's here to solve some specific problems. Yeah, and I will say that there are also some examples as well in Japan traditionally. Also a place in which, as we know, there's a lot of earthquakes, and that's why you can see also here a lot of pictures regarding these microgrids. No, and one of the things that I like to present, not because it's nice, but because it's an example of what happened in Japan when we had the Fukushima disaster, and it's just that we had a microgrid system working in island during 3 days. So I will say that this is very important also to show here that technologies that work with solar, battery systems, in that case it was some natural gas generators, can survive a natural disaster that nuclears make. So if in the future they want to tell us, don't worry, nuclear is here to save you, we know that this is not possible anymore. So we cannot accept this. Yeah. So countries like Denmark, we never had nuclears, and it's clear that it's not. It was only once in the agenda of one politician, and he was totally destroyed in the political level, let's say. So I think that we have to be very clear with this and very tough. Behind these ideas are, we really want to go on renewables, and we are also critic. We have to have our self-criticism with the technologies, let's say. We know that we are not 100%, let's say, clean, and basically to be 100% clean, it doesn't exist, no? It's maybe the natural die. So we have to also understand that. If you need also more information, I'm very much in touch also with these guys of this microgrid in Japan, so I can also pass to you the information if you want. Another important thing is about the operation of microgrids. Yeah, a lot of things has been done, I will say, and you can find a lot of technical papers, but if it's in a paper, it's better don't believe it, right? So I will say, believe it if you can see in a real site and working for many years, then we can talk about that. One of the things that we were at the beginning, let's say this change of paradigm and talking about microgrids, and this is something that we saw exactly at the beginning of 2000. It was like a microgrid was defined as a system that can work connected to the grid, what we call grid connected, and could work also in island. Right now, the reality is a little bit different. It's true that we have the two operation modes, but what we have is, or what we are seeing is that a lot of these microgrids or work always connected to the grid, or works always islanded, depending on the conditions. So this is what is happening. Only I will say that there is maybe an exception in some places in which there's a constant blackouts, and they have to deal with that. But this is not the normal situation. Normal situation is that maybe you could have suddenly a blackout, and then you have to manage, let's say, this islanding operation, and maybe you need to detect it. And sometimes detect this is not so easy. And again, you can find a lot of methods that works to detect that you are in island. But basically, if they are two units using the same method, they will, if there are active methods, they will interact each other. So finally, this will not work. Yeah, and you can make all the science that you want, but the more units are in the grid using the same method, the more difficult is going to be. We can, and they will always let's say, interact each other. So I will say that more and more islanding issues are coming more from the utility, and maybe we will need the signals from the utility that will come and say, hey, there's a blackout here, there's this problem, please disconnect this part of the grid from the main, and let's do something. But that's, of course, something that we cannot do alone, and needs still more coordination. This is another example. I think that here this example it's very nice because I guess that in Nepal you have a lot of areas similar like here. It's a rural environment, and we talk about a small city in which we have many part of the people is working outside, let's say, in the rural parts, and then they are basically using the city for their houses. So the construction of this was also through an EDO project, so it was financed by Japan as well, the same as the microgrid we saw from Fukushima as well. So here you can see all the power. Let's say it's basically battery systems, PV, and then there is a diesel genset. I have to say that I hate to erect diesel engines, but sometimes it's necessary. If it's possible, you could increase, let's say, the energy storage systems, and maybe diesel engines could be, for instance, starting once or twice per year, like in some facilities. Then it's fair enough because you can save when you have a lot of days without sun. But in that case, it was a little bit, a little bit too much. So I will say that this is an old-fashioned microgrid system, but still you can see the idea behind that. We have around 90 kilowatt peak of consumption during the night. And then that's why we have this engine with a peak of power of 100 kilowatt. We have the solar PV at 70 kilowatt and the batteries with 80 kilowatt. Yeah, you can imagine that if we think about how nowadays we build microgrids, it will just, maybe the engine will be a small one, and then we will size a little bit higher all the solar PV, of course. So here you can see what happened. It's very interesting to see that at 7 o'clock we have to start the diesel generator, but of course this diesel generator gives us more power than we need. At that moment, the solar cells are not giving enough power for the peak of consumption here that you can see at around 40 kilowatt. So what we do? We store the rest of this peak to the battery systems. That could be very nice because we are working with the diesel generator with a more efficient point. So let's say that if we think that in that case 70 kilowatt is the more efficient point, it's pointless to work, for instance, at 20 kilowatt because it will be basically produce a lot of losses. So we go to the better point that we think that can work, and then we store the rest inside batteries. Yeah, so that's kind of nice. It's not 100%, let's say, optimum, but it's one of the possibilities. The other thing is about control. Again, when we talk about control, I will say that we reach the saturation on the research side. And right now, all these ideas are already implemented in many devices. Yeah. So don't think that we are talking about rocket science. What happened here is, like, imagine that before I have been talking about battery systems with an inverter, and this inverter fixed voltage and frequencies. And we had many other converters connected typically with, for instance, solar PV or a small wind turbine like we have in our facility, and they can be seen as current sources. This system is very good and, let's say, in general stable. But what happened when I have, for instance, a couple of battery systems or battery packs? Yeah, when we have two battery packs, then the problem is that if they try to enforce voltage and frequency in the same node, they will basically fight each other because normally you have a small difference on the voltage you want to apply on terminals. So this means that huge currents will flow from one battery to the other. And this is a problem also because you could see how one battery is discharging over the other battery, which is not nice. And the same with the frequency. So right now also, I will say that a lot of battery solutions are appearing in the market. And we have been, and still we are right now starting a new project with a German company, also to develop this kind of, let's say, multi-home battery systems. Yeah, and the way that we do is very classical. So it's by using frequency droop control. So this droop control, I think that first time I saw this was in something like 1999. And at that time I could not understand very well how this works. And we had to implement this in a UPS system just to avoid, let's say, intercommunications between them. I understood that this is how the diesel let's say the synchronous generators operate. So basically when you have synchronous generators, you ask this synchronous generator for more power, automatically the frequency will go down. Yeah. So this means that there's a correlation between the power that you give and the frequency. Because the frequency in your power system is the same, automatically they will give proportional powers to the grid. So that's how also on the other way around, how they work as, let's say there's a natural synchronization between them. And then that is also why it's beautiful somehow, no? When you think about our big power systems, all these synchronous generators are naturally connected. There's a natural connection between the power and the frequency, and everything is harmonized, right? So when we had more and more renewables connecting here, in Europe, in a very early project called VSync, they start to look on how we could add also inertia to renewables. This was kind of easy when you think about turbines, because of course it operates like a flywheel, so you could store some energy there. But when you think about photovoltaics and so on, there's no way that you could add inertia, but adding extra energy storage systems. So there is not any magic behind that, right? The only thing is that you have to implement this in a DSP or a microcontroller. And well, it has been many people try to also implement different ideas. Yeah, but all those ideas are finally the same. Yeah. An example, I don't want to bore because I know that a lot of you know this example. The cool thing of this example is that also comes from Japan. Yeah, so you know that people in Japan, they make a lot of crazy things. And this, I don't know if I will be able to run this video. Yeah, these are a number of metronomes, you know, for music. So this is the old-fashioned metronomes. And this is for getting the time in music. Yeah, right now we have electronics. So with electronics, it will not work. Yeah, it's kind of funny because if you repeat this experiment with electronic metronomes, it will not work. For some reasons, here you have 32. Yeah, you have 32 metronomes. It has been repeated for 64. I have also the demonstration of only 2. If you want to make only 2, it's very easy. You just put a small table of wood, put a couple of tanks of some cola or whatever, yeah, and then you put a couple of metronomes up, yeah. So when you see the equations, you will see that really they act like droops. Finally, they are synchronized. I have no way that we could stop this, but finally they are synchronized. Yeah, all of you know this. So what happened when we have, let's say, systems that don't have this kind of operation? What we have to do is to implement this. And look, if you think that we have, for instance, a couple of power converters, and we use to have the frequency of reference from one and the other, when you are programming, imagine that you fix the frequency to 50 Hz, ideally it will be 50 Hz. What happened in reality is that you are using a clock. So this clock is made of quartz and produce some vibrations, and then you have some ppms, so there is kind of an error. This creates an error. So first we have an error in the clock. And the second error we have is the discretization error. Imagine you have a 50 Hz signal. When you implement in a digital system, if you want to use, for instance, 8-bit of word, to simplify, it will be 1024. So this means that 50 Hz will produce an error of around 5 millihertz. This 5 millihertz, when you start the system, maybe in phase is not so big, but after some minutes, they will go out of phase. Yeah, so that's why we need this corrective action. The corrective action appears when we implement those kind of virtual inertias. Yeah. And when we implement those kind of virtual inertias, means that the frequency is dependent on the power, especially when we are disconnected from the grid. But don't think that the frequency is fixed in the grid. Also, the frequency in the grid is changing all the time. Yeah, this is something that you could be surprised. You make some measurements, and you will see more or less that every several seconds, the frequency is going up or going down. Yeah, and this is because, for instance, the grid is overloaded. They are generating too much power. Frequency starts to go up. And now what they do is they reduce the power, and you can see how the frequency is going down again, and vice versa, right? So this is what we call in big power systems secondary control. This is one example from Nordic countries. Yeah, I always use this example because you can see that this is kind of a dead band of acceptance. Let's say that in plus minus 50 millihertz, but if we are out from here, then what we have to do is to respect, let's say, this form. And if you think about this form, is something like the response of a PI controller, right? So what we are doing somehow is to enforce the systems to go here with a PI controller, and once we are here inside with a dead band system, we will just maintain this frequency. So those secondary control are just implemented by a PI controller plus a dead band. It's kind of easy, right? So this is what we saw in big power systems with the secondary control. They are basically taking a look on how is the frequency all the time. They don't have to measure anything else, just the frequency. So it's local measurement. And then with the SCADA system, they compute how is the frequency error. So they more or less know how is the power imbalance, and now they can readjust the power from their generators. Yeah, there's a lot of products about this, a lot. Yeah, so you can see people selling secondary controls very fast for the market, which is not easy because, you know, it's not about control. Yeah, don't tell me now I know that a control will be very fast. No, it's useless. What has to be very fast is the generator that has to deliver the power that is given as a reference from this secondary control. So small generators or even big generators that are able to inject a big amount of power in several minutes, within several minutes, that is something very important that the big power systems needs. Now, when you think about microgrids, it happened kind of the same, very similar. But in our system, because we talk about small system, still we can achieve even faster ones. But it's very important also to think about which are going to be these units that are going to supply this secondary regulation as well. So we can do this in a central way, and we can do it in a decentralized way. I will say that when you think about automatic control, try to do things like secondary control, it's kind of easy to do it in a distributed way. Yeah, just using some communications. You have distributed controllers, everything goes well. When you think about optimization, even in theory, you could distribute as well. I would recommend it to do it in a centralized way, especially when we think about small systems. Yeah. As I said, everything is possible when you make a simulation, but then you have to also think about reliability and possibilities. And I'm not against, we are not talking about the same as we said before, AC or DC, you know? It's like, okay, sometimes it's AC, sometimes DC, sometimes both. Here is kind of the same, right? So there is nothing bad about centralized controllers, absolutely nothing, right? So you have higher levels of controllability, and there is nothing wrong about distributed control. You have higher levels of reliability sometimes, but also it has a lot of problems. Yeah, it relies on, you have a lot of maybe traffic of information back and forward. So So be careful also about that, because you can read a lot of things that bias you from what is the reality and what is, let's say, possible inside some very controlled environment. Yeah. Oh, here you can see a little bit more. If you think about primary control, I will say normally is decentralized. Decentralized means don't need communications. If you think about secondary, could be centralized or could be distributed. So distributed means it's not pure decentralized, but it needs communication overlaid. And tertiary control, even if it could be distributed, I will recommend, especially in small systems, to try to have your small SCADA. It helps a lot. Yeah. So this means that also microgrids could be also built in places that we don't have any grid, and we could connect a number of microgrids. And I will say that this is nice. And one of the challenges I will say is how to coordinate them, but without using a lot of very complex systems. So do it in a very easy way. So thinking that this is every of your microgrid is like almost like a generator, let's say production and consumption, and seeing them as a block, and try to don't make too much problems, especially to the DSO if we want to also interconnect them to the main grid. So the more their behavior, it's more like a synchronous generator, the better the grid will accept it. That's why when you try to make all your system behave like a system with inertia, then it will be very plug and play connected to the grid. Yes. Because also the grid have the same levels of control at the same time, but maybe reducing scale. Yeah. It was indeed my fault for lack of imagination, just taking the ideas from the big power systems and say, okay, I'm going to adapt exactly the same scheme to small microgrids. Yeah. Another important thing is the whack-a-mole effect. Yeah. When you think about how you can solve problems like power quality, harmonics, and so on, you try to solve this locally. And it works very well when you try to solve it locally. But when you think about globally, and this is something that happened in Japan, they try to install active power filters in some part of the grid. Then the THD reduces in these parts. But what happened, like the whack-a-mole game, once you reduce the harmonics in one part of your grid, then absolutely will increase the harmonics in other parts. So it's kind of funny because in low voltage distribution systems, we have harmonics problems, but nobody's paying for that. So in the market, there is not active filter working on low voltage. In the medium voltage, also it happened the same. We pass to when we pass to distribution, automatically we'll have almost pure sinusoidal waveforms, maybe with some background harmonics. So also you cannot see in such a high power systems, active filters. It will be basically passive filters. And believe me, there is nothing bad about passive filters. Not in a simulation, but in practice, you need to also think that a power converter, it's very, very expensive. And when you scale up from kilowatts to megawatts. Yeah, I already explained this. Another important thing is regarding what happened with DC. Yeah, there are some data centers that also are going to DC, but I will tell you that this is a minority indeed. Yeah, it's very curious because you can see a huge amount of documents appearing about DC data centers because of their novelty. But if you see about the results, we are just talking of improvements up to 10%. Yeah, even people make some studies, efficiency improvement, as you can see here, 7%. Yeah. So, and those are only maybe data centers that can supply, let's say, the energy by themselves. For instance, you could see some data center like Intel that they produce their own electricity, so they basically disconnect from the grid, and then maybe it starts to make sense. But still, you have to think that there's a lot of loads inside the data center that works on AC, and you will say yes, yes, because you have to imagine that the loads are electronics equipment or communication equipment, which are DC. You have a lot of cooling systems, which are normally around, could be 30% of the amount of power still working on AC. So not such an easy thing. At the same time, a lot of people believe maybe 15 years ago that we could have DC residential systems. Unfortunately, it's not. Well, unfortunately, or who knows, but everything goes to natural stage, you know. We made some studies in the past, and we see that if you're not able to produce your own electricity from solar cells, store it in battery systems, and consume inside your house, if you are in this situation, you can gain up to 10%. If you're not in this situation, you're only having, for instance, solar panels, but you still have a connection to the grid, you even could have losses up to 10% if you're connected to the AC grid and then convert to DC. Yeah. So there's no question about this, and you can check it when you are coming back home. In some places, like for instance, India, appears some places in which maybe DC microgrid solutions could make sense. But I will say that it's not a majority. Yeah. Some maybe residual camps in some places, we saw it, but it's really small places, maybe in Africa. So that is the reality. It's not, DC is not exactly going home. Yeah. But many ideas were developed for houses, let's say. For instance, this was another colleague that was here as a guest in our center when we just starting, our friend Kakigano, and he was developing bipolar DC systems. So basically having plus minus 170 volt for distribution. So it's like having a three-phase system over DC. So 0 plus minus. It was a very good idea. And I will say it's totally non-used in a house, but right now it's implemented in Lappeenranta in Finland as a distribution system in plus minus 700 to 800 volt for distribution. This is connecting a number of 5 houses, isolated houses, let's say in the middle of nowhere in Finland. And finally, of course, you need a DC to AC converter, because of course those houses are working on AC. Anyway, this is maybe the exception that confirms the rule that we are not going on DC in residential applications. Yeah. For another example, Aribas was another company developing DC distribution systems for houses, and it works well technically, but you know, the reality is not, again, going here. The good thing that has been developed here is to use voltage the same way that I showed you before with frequency. Yeah, if you see all the renewables connected to power converters, let's see how the voltage is, let's say, changing. If the voltage is very high, means that we have too much generation, so we are going to reduce it. So the same frequencies from the same concepts that we have on AC on frequency are implemented here in voltage. So this is very nice because those ideas, of course, has been exported to other places, not in houses, but other DC microgrid systems. Another important thing is the rise of electric vehicles. And maybe you think about electric vehicles, it's not only having a big car. We can see some places also with electric bikes and so on. So electric appliances are coming more here. Even you could think that the idea of having store energy inside your electric vehicle could be one possibility. Also to have, let's say, what we call home battery systems or stationary batteries are having more and more importance. So this is just one example from Fronius, our neighbors in Germany. You could have, let's say, batteries at home. As far as I know, it was also an agreement with Powerwall, which right now has been moved to BYD. As you can imagine, a bit cheap, but those solutions are very compatible also with grid-connected PV systems. So you can see here how we have conventional grid-connected PV systems, and then we have hybridized, like PV with battery, and then we have at the same time switches. Now we have a lot of these converters can operate also disconnected from the grid. So once the grid is out, you disconnect your main grid from a switch, and you can maintain the power inside. Let's say if you are above 500 watt, it allows the system to still work. If it goes below, of course, you have to shut down the system. But what is not acceptable is you have a shining sun and you have to disconnect your system because you move to island. Okay, another important also work that we are doing here is going also for reduce the emissions in ships. No? And I will say that this is very important because right now you know that we are reducing a lot with CO2 emissions in flights, which is something that I really like. But at the same time, there's a big challenge to reduce the emissions in the ships. If you look globally, we have 3.42% of CO2 emissions coming from, let's say, the flights, but something similar with the ships, 3.15%. Yeah, it doesn't mean that the contamination is higher flying or going on ship, of course, but in that case, let's say globally, this is the situation. Yeah. Because of that, also a lot of ships are moving to electric. This is the biggest in the world. The biggest, in that case, is the biggest ship to carry, let's say, containers. And of course, it's Chinese. And you can see here, it has a 2.4 megawatt hour battery system, and it can cruise for 80 kilometers. Yeah. What happened exactly with the ships? You can see how traditionally we had segregated electric plants architectures, like having the propulsion systems and what we call the hotel load separated. But more and more you have them integrated. So you can see in some cases, that's very important, in some cases that we are going more to electric. The way that we are going to electric, I will say that is not the most sustainable way, because we are using diesel generators to produce electricity to move electric motors. The advantage here, respect to the traditional, is that we could make our engines work on the best operation mode, most efficient way, let's say, and then part of the electricity we could manage with the batteries. Yeah. So yeah, this is just some examples. And of course, this has been a game changer, the use of energy storage system in this kind of cruise vessels. For instance, one of the most famous is the Queen Elizabeth. It had a number of 9 diesel generators. And the problem was that was a short circuit in the main bus, and the whole system went down. Yeah. So this is really a problem. And that's why right now major part of these vessels has 2 separate buses. So you have 2 separate buses. And in case of any problem, you just open and you disable one of the buses, and then the other bus can still work. Yeah. And well, that's let's say a world itself, but I will say that also multi-microgrid systems have more and more interest and attraction here, and there are even some standards already working. Again, the problem with AC and DC is there, And the main problem, again, trying to go on DC to make it more flexible, is when you increase a lot the voltages, then protections are not there. One of the things that we are proud is to have been developed the first hybrid electric ferry in Asia, which is called Happiness, and it's placed in Taiwan. So it's basically a European technology right now from Danfoss. And well, it's a huge amount of passengers every day, more than 5,000 passengers every day there. And we put battery systems there and a couple of diesel generators. But right now our goal is to increase the battery level and to just move on electric, because it's just a very short distance, let's say. And here you have some examples, some photos of this ferry. So here is the electric motor, and here is the battery pack. So I think that this is kind of nice. Another project we did also was, because we have more electric ships, also those electric ships maybe have power quality problems. And right now these standards are very tough with that. So they are asking us to reduce the frequency and voltage transients, let's say, variations also. And at the same time, it's not acceptable to have more than 8% of THD. And this inside the ship is very complex because you have a very weak system. Yeah, and we made our test in this ship, the Horizon 2, which is in Poland, and it's normally having a, let's say, trips to the North Pole. And you can see here some pictures about the diesel generators, the pump for the water, and so on. So 3 diesel generators, all the loads, let's say here, and here was the pump, water pump, and then this is the main thruster. So it's a very simple structure in that case. Yeah. What I can tell you is that due to the pump start and stop, we had huge peaks. But we could see that even in the case of when the grid is balanced, everything is fine. But we just made some tests making a slight imbalance, like 1.5%, which is very, very acceptable for the grid. But we had a lot of problems in the thruster when this imbalance occurs. So things that maybe in big power systems are acceptable, in this small microgrid not acceptable. Yeah. Another of the research we are doing is about cold ironing. So what happens when I have ships going back to the port? They pollute the area, not because maybe they are electric, they just need some electricity for their freezers. And right now they are obliged to stop it and to have the connection to the main port. So also this means that we have to put more and more electricity resources in the port. And the way that we are thinking it is to put more renewables inside the port and to have more electric, let's say, transportation inside the port. This is the way that we are, together with the port of Aalborg, thinking on renovate it. And I will say that this is a global trend in the world. At the same time, you could see, and we have the same problem here in all, we have some of these cranes using diesel generators to generate the electricity for the cranes. Yeah. So we are again polluting because we have to generate electricity, let's say, in the site. Right now, what we are trying to develop is a system to use part of the power, let's say, that we are generating from the cranes to supply other cranes or to supply other parts of the port. So I will say that this is also a global trend. Also, we have some colleagues in the United States also working on that. And I will say that all we have to make a huge effort to make it more clean. Because we finish with the Earth, so basically land-based microgrids, maritime microgrids, then we go to the space, and we have also some colleagues working also with nanosatellites. We have a nice company here in Aalborg called HomeSpace that they develop nanosatellites, so very small satellite systems. And we are developing with them some of the electric systems. You can imagine that this is kind of a DC microgrid in which we have batteries very special because, of course, you have cosmic radiations and so on, and very low temperatures. But I will say that is a very nice research that we are developing at that moment. Also, very important research we are doing is with collaboration with the University Autónoma of Barcelona. And this is a project in coordination with the European Space Agency. And what we are doing here is to use some ideas of control of microgrids to use in space closed ecologic systems. And this is not connected, let's say, with an electric microgrid. Indeed, a closed ecologic systems, you mean that you have an ecosystem, maybe with animals, maybe with vegetables and so on. They can coexist, and then basically they don't need anything extra from outside, except, of course, maybe light from the sun, but nothing else, right? So it's like a man-made ecosystem, yeah. And one of the more advanced examples is in Barcelona, and it's the pilot plan that also the European Space Agency is doing to also prove concepts that then they will go to the international platform and to the future Moon and Mars base. So how we do this is we try to fix the oxygen concentration in a very tight references. So now you can think about references again, no? The same that when we try to have tight voltage and frequencies. And then we have a number of compartments. So we have some compartments with anaerobic bacteria. We have also some small reactors. And you can see also here we have the plants that also they make the photosynthesis. And you can imagine that part of this photosynthesis is to generate oxygen that finally is for the cabin crew. And then the crew, of course, when they pee and they poo, they generate all these nitrites that we have to treat in other compartments and finally to give back this oxygen. So it's really a closed system, yeah. Maybe you think, okay, that's nice. These are some pictures about the nitrification compartments and the photoreactors. And here you can see also all the plants. And in our case, the crew compartment is just some mouses. But finally here what we have is a closed, let's say, closed loop system in which we measure oxygen. We want to have some setting points of oxygen. There are many other setting points, but we just neglect here. And then we adjust how much light we need here to process these nitrates and make, let's say, the process exchange between oxygen and CO2. Yeah. So it's very important that we reach this oxygen to exactly to this 20%. Yeah. So you can see a lot of parallelism between closed ecologic systems and microgrids. For instance, when we talk about photosynthesis, kind of parallelism with the photovoltaics. When we talk about oxygen storage, in that case, we have one compartment to store also oxygen. It can be seen like what we do with storage in microgrids, and also the micro fuel cell can have some parallelism with fuel cell. Here the problem is that in microgrids, maybe you could have orders, let's say models with orders. I don't know if you have one converter, maybe order 2, order 3, or 30 in the worst case. In our case, we have to say that we have compartments having more than 50 variables. So maybe the whole system have more than 200 state variables. So it's really complex to control. But finally, we develop also, let's say, a hierarchical control to control those systems. And I will say that's very nice and amazing. And you could see also how hierarchical control is also applied to this kind of closed ecologic systems. This is the most amazing research we are doing here also with our colleagues that are also connected to this seminar. So thank you. And finally, I want to finish with a statement of Max Planck, who was one of the first to look at quantum physics. He said, when you change the way you look at things, the things you look may change. Thank you very much. I think that's all from my presentation. So if you have questions, I'm here to also discuss with you.
Thank you, Professor. We will.
If people write some questions, I think that there's some questions. I can read it if you want, and I can start answering.
Okay. I will read you for you. I will read it for you.
Okay.
No worries. Thank you, Professor, for your presentation. It covers from theories to application of microgrid and renewables with this control. Now, I look for questions from the participant. I will take one by one.
Sure. I think we have right now around 100 participants also, so maybe they could also raise some questions or raise the hand. Even.
Yes. We
have a
ask
question
participants
from
to raise hand so that they can ask themselves.
I want to request all the participants to raise their hand. If they want to ask their question in their own voice, I will also unmute them. First of all, I will. We have a question from Sunil Kumar. Professor, I want to read it. During the initial stage of island mode, startup can cause a certain intake of current, which can affect the frequency of system and voltage. This can cause the generator to trip and go offline during the initial phase. Sir, what steps we take to encounter this problem?
Yeah.
It is asked by Sunil Kumar.
Yeah. Thank you, Sunil. I think this is a very good question. This is what we call also black start operation. So black start operation is the way that we start the power system, and this in big power systems is very clear. So they have a protocol established to start slowly. Otherwise, it happens what you say, that you suddenly start up, you have a lot of frequency variations, and the generator just trip. So you have to establish a black start operation, and this can be done in the SCADA system. So to some generators and loads to enter sequentially. So this way you start smoothly. If you start to, as you say, if you start trying to make everything at the same time, it's going to affect it. So that is the point, to program it sequentially. And this changes from microgrid to microgrid. So I cannot give you a general answer. You have to proceed and see how the power can be smooth, and maybe you have to come back sometimes because you saw that it had some problem. But I will say that you just program, you start one generator, putting some loads, start next generator, putting the rest of the loads, and then you ramp up and ensure that it's stable. I don't know if I answered his questions.
Thank you, Professor. We have another question from Ramus Resta. Is it necessary to make a local load dispatch center LDC for microgrid control?
Well, it depends on how big is the microgrid. But when the microgrid have certain dimensions, I would recommend to have it so that we can control well the load part of your microgrid, especially when you have these big, let's say, imbalances. And then this is also connected with the previous question. When you have an isolated microgrid, if you start to have a lot of power fluctuations because the grid is very weak, you may have a stability problem. So I would recommend to develop this load dispatch center when the microgrid starts to be a little bit complex.
Thank you, Professor. There is another question from Sunil Kumar. How you are balancing between generation and load in island mode?
That's a very good question. We balance generation and load by using the frequency. So we have the same principle as in the big power systems. When the frequency increases, we see that there's more power generated than load. Then what we have to do is to reduce it. It's natural. The only point here is that there's no difference between big power system and microgrids. You have microgrids that are basically very resistive. Yeah, the line is very resistive because we think about low voltage. Then when we go to big power systems, which are very inductive, you have to imagine long lines, transformers, machines, inductive. Then active power is coupled with the angle, so that with the frequency. However, when you go to distribution system like microgrids, active power is more coupled with voltage. So you could also develop the same system, and we did it also for some products. You develop the same system looking at the voltage and regulating the power. So you have to see how is the behavior of your microgrid. A lot of power electronics and LC filters, not LCL, because this L adds extra inductance. Then you move to, let's say, voltage active power control. Yes. Yes.
Can you move to the another question now?
Yeah, of course.
There is another question from Subrat Daral. I'm intending to do further research in power quality issue.
You are addressing. So it's not the same if you go to a ship that if you go to an islanded system, or what you have there, you have diesel generators or not, you have power converters. So there are many things to see. But I will say, try to go as simple as possible. If you go to medium voltage, try to work more with, let's say, passive filters and not so much on active, let's say, because as I mentioned before, there is not market for that. So you have to also take a look. But I will say, contact me and we could try to find a study case for you, and we could take a look what is exactly the power quality issue. I will say that it also is important that we have unbalance, because as we think about 4-wire systems, you have some unbalance. Sometimes important, sometimes not. So it depends what you connect also there.
Thank you, Professor. We are receiving so many questions. Many participants has raised their hand. We will
also raise the hand.
let them speak after. We will let them speak after taking some question we have got here.
Sorry?
Professor, there is one question from Hussein Menon. Sir, can you guide about off-grid microgrid control strategy for power management and stability?
Well, this is very general. I will say that this is research in general. So I would like to focus a little bit more. As you can imagine, there's many control strategies for power management and stability. So I think we have to discuss more, because this is, I think, too general. There is someone that say, can you explain more about BSG and how that could be invented? I think that's very interesting. Virtual synchronous generators, it's like having the equations of a machine and implementing in power electronics with a DSP, digital signal processor, right? We demonstrate that if you take a Druck controller, very easy, and you add a low-pass filter, it will behave exactly like a virtual synchronous generator. So it's very easy, just one line or 2 lines of code. One filter and a frequency Druck. That's all. Yeah. So, because it's simple to answer.
Thank you, Professor. We have another question from Mohammad Numer. What are fields of improvement can be obtained by using some advanced ICT microgrids, efficiency of energy management, and improving power quality? It is asked by Mohammad Numer.
I think that this a lot of questions in one. IoT, yes, we have elements of IoT inside the. You could have elements of IoT inside the microgrid. The only thing you have to bear in mind is, do your system have easy internet access or not? So you could use it. And then what's a device that is in an IoT cloud if you have a local controller? So I will say yes, it's possible. I will say yes, because you could have this in the cloud and you could have a lot of computations in the cloud, but I will say not exactly to improve power quality. Maybe in some cases, but I will not generalize.
Thank you, Professor. Now I have unmuted Sunil Kumar, who is wants to ask you question on his own voice. Sunil Kumar, you can speak now.
Hello, sir. Can you listen me?
Yes. Hello.
I'm fine, thank you. I'm from Pakistan.
Yeah.
Currently working in a power plant. Sir, I have a question regarding to this microsystem. Basically, the feeders which we are using for this microgrid system, are not as much compatible as we are using for the generation system. And you can see that these microgrid systems gaining the popularity, and the feeders which you are using are not that much compatible. So can you please elaborate something on the design of the feeders which may be used in the future for these microgrid systems?
Thanks for your question. Indeed, what you are saying is totally right. If you go and you install your microgrid system, normally you will not have inertia yourself. So it's very important that for the future, those microgrids can provide inertia in the PCC. So in common coupling, we can see them as a voltage source with inertia. Secondly, it's important that those microgrids try to solve the problem locally. I'm saying this because I can see a lot of people thinking that the microgrid will provide power to the grid. And this can be very nice in theory, but in practice, our feeders are not, let's say, designed to absorb power.
Yes.
So we are doing this in some very controlled situations in which we have solar PV, and then you have a special contract, and okay, agree. But I will not say that this is like a big party of microgrids, let's exchange power, because this is going, as you say, to the feeders, create problem also with the protections. So I would recommend also that a microgrid should try to solve the problem locally. Don't be a trade for the grid. So if we can just focus on these two things, try to cover locally as much as possible your demand, and if not, you store it for later, then it's fine. Yeah. So that I will say that for the existing feeders, we have to go in this direction. And the second one is the inertia. So adding the inertia. So you as utility, you just see it like a synchronous generator. Then everything will be more easy.
Yes, I understand. But sir, there is a problem when the fault current in microsystem can reach the maximum higher than those faced in the distribution system. Then there are many chances comparable. We will compare the magnitude for that load current, and that will severely damage our whole microgrid system. So what steps we will take to encounter this problem?
You have, of course, to redesign the system and to think in the way that you could also eventually just disconnect the microgrid if you think that you are going to damage it. So it can prevent against these inrush currents.
Yes, got your point. Thank you.
Thank you.
Thank you so much, Professor.
Thank you, Sunil Kumar and Professor. We move to the another question. There is another question from Nabil Muhammad. In island mode, reactive power sharing is problematic, especially during high RBX ratio. What methods do you suggest to mitigate this issue if we operate in distributed mode only? I think you have worked much in this issue.
Yes. Okay, let me explain a little bit. If you think about a microgrid, I don't see any special objective to have a perfect power sharing. Let's say, if you think about reactive power sharing, it doesn't matter. When you have two generators, if you have a reactive load close to this generator, the most efficient is that this generator provides local reactive power. If I have to transfer at a distance to another load to make a perfect reactive power sharing, it makes no point. So I think that we made also studies some years ago with a big grid with a lot of nodes, trying to enforce reactive power sharing or just don't doing anything. The conclusion was it's better don't do anything, because automatically you will provide the reactive power to those local loads without creating a mess with a lot of losses. So I will say sometimes you have to follow the path of don't try to make the things so perfect, because sometimes the objective that you have, you don't know why is this objective, you know, because you say, I want to make a reactive power sharing, but why you want to make equal or proportional power sharing? What is the objective? Maybe if you think in terms of losses, it makes no sense. Yeah, and what you do is to do the things more complicated. So I would say don't care too much about reactive power. Just let it flow. Yeah, from inner to the generator to upside, and I will not recommend any special thing.
Professor, now there is another question from one of our participants. It's a general question. What are the major issues in microgrid protection, and what are the general practices from one of our participants?
Yeah. If you take a look on the, let's say, on the traditional way that you design protections, you have defined different zones or areas with different times, from one point that you think that is the generation to another point that is the load, and then you can start disconnecting parts of these different areas. In a microgrid, what happens is that basically loads and generators are all distributed along. So you cannot make this kind of separation, and this is a little bit more complex. So this means that you need bidirectional sensors and switches, and this bidirectionality, let's say, makes the system a little bit more difficult. The second difficulty is that our generators don't have inertia again. So they are very, if you produce a short circuit, for instance, they are very pro to maintain the voltage. And I think that it's also very important that all our generators are well protected against this. But the first protection that you have many times is just you trip. So maybe you create a blackout. And this is a problem. That's also a challenge, let's say, to have very fast protection systems, and we know that this is linked to have fast communication systems. Yeah, so this is also much different that from the big power systems perspective.
Thank you, Professor. There is another question from Pritam. How much it is difficult to regulate reactive power in a hybrid microgrid? It's again a question
Exactly.
of reactive power.
If you have an interest in the DC part, I will tell you, don't care about the DC part because you don't have reactive there. And about the AC part, just make it as we said before, trying to balance a little bit the reactive power with droops, I would say is good to avoid voltage collapses. But it will be very natural to do it like this. So I will say that if you just implement some kind of, in that case, reactive power droops, it will be fine. But I want to say something also. If we think about a microgrid, it's basically very resistive. So this means that reactive power is coupled with voltage. Many times, just using a virtual impedance, it's enough to have acceptable reactive power sharing. So I will say that even don't make it too complex. Let us, let's say, reactive power, when you have active power and voltage, of course, more resistive, then you could solve it, let's say, with the virtual impedance, as I said. But I think the phase frequency. So automatically, if you have these inertias or let's say droops, it will solve the problem. And very precisely, because in big power system maybe it's more difficult, but small power system, reactive power is not a big deal. It's very easy.
Thank you, Professor. There is another question from Guy Dubur. What are the protection strategies for microgrid since fault current are different from grid connected and islanded mode?
Yeah, of course, if you have let's say the fault currents, when you are grid connected, you could have suddenly that maybe the grid trends to provide all the power needed when you have a fault. So that could be a problem, and then you have to deal maybe with the grid disconnection in some cases, or disconnecting, let's say, isolating this fault. While when you are in islanded mode, you have to support that, and sometimes the grid, let's say, is very weak. So then you have to try to maybe isolate the fault before you start going very low in voltage, let's say. So yeah, there are basically these two differences. So I will say that selecting appropriately the circuit breakers, it can be solved.
Thank you, Professor. There is another question from Russell Mahmood. In a microgrid with mostly power electronics based source, are you concerned about the controller interaction?
Sorry?
Concerned about the controller interaction when mostly working with power electronics based sources.
Okay, yeah, of course. Of course, you have a lot of power converters. So you could have a lot of interactions, especially high frequency currents. A lot of high frequency currents can flow from one to the other. So, and this is really a problem. Beyond when we talk about fundamentals like active, reactive power, everything it flows well if the control is well fixed. But you have high order harmonics of frequency that cannot be controlled by the converter because they are beyond. And that's why it's very important to have a good design of those filters and to try the interaction, because normally those components are well tested in laboratories independently, but once you try to put them together, it will be a lot of phenomena of resonances, but understanding it as the interaction between those. high frequencies that we cannot control. They are outside the bandwidth of our converter.
Thank you, Professor. Our another participant is asking with greeting. Please describe in brief on the control strategy on low inertia system and stability issues.
Well, I don't know exactly what the person who asked wants, but for the description, I think I will need maybe half an hour to explain again. So I will say that what maybe he or she should need is to see about something about power electronics control, very basic, and then adding communications, and then see what we can do also with, let's say, in the SCADA level. But it's a little bit long to answer.
Yeah, we have to take so many questions. We will just two questions onwards. There is another question from Imal Chaulagai. How do microgrids deal with uncertain ups and downs of wind and solar power?
Yeah, that's a good question. Indeed, uncertainties of solar generation or wind, when we talk about a wind power microgrid, are very important. And what we are doing here is we are taking into account those inside our energy management system. So our energy management system has to be tolerant to those uncertainties. Of course, you can imagine that increasing energy storage is one way, but very expensive. But also, if we are able to predict those uncertainties and to know exactly which are these ranges and to test that our system still can work, that is something very nice. And this topic that also on that.
There is another question from Ram Pandey. Can you explain how protection coordination module works in microgrid feeder fault, utility fault, and resynchronization?
A grid fault, utility fault,
and resynchronization.
Okay. Well, basically what we have here is that maybe you have a fault of the main grid. Then we need to detect that we are in island, and it's not easy because the grid, it has a component, at least for instance, the energy storage system is trying maybe to fix the voltage and frequency. But sometimes it's not like this. Sometimes we can see systems that are just working like a current source. And then it's very easy to detect because you can see how your frequency is just going down or going up. So the frequency is going out of the margins. And then you can do it just with an algorithm to detect it. Then once you detect this, you have to take care of your voltage and frequency locally, let's say. So that's the basic thing. Then once you see that the grid is present again, you need to resynchronize. Normally, I'm not saying that is easy, but depending on the distance that you have between your grid and the element you want to synchronize, if it's a diesel generator or it's a converter, you need some communication module with the place that you have the switch. Some clever ideas I saw in the market is like some inverters having the battery system and the switch integrated inside. Then it's more or less easy to make the synchronization because we know that in the market there are many solutions that finally they rely on cables. Yeah, so maybe you need some cable to make the resynchronization. But resynchronization normally it's done by a slow PLL, let's say, to make it summarized. We don't need very fast PLL systems, but just slow PLL that we are sure that the phases are locked, and then we just synchronize. I'm saying this because you can find a lot of PLL systems that are very fast, accurate, and so on, but because they are working all the time with the grid. Yeah. In our case, just slow, let's say, slow, but with high accuracy systems is enough. So that is the process.
Thank you, Professor. Because of time restriction, we cannot take more question. We will forward the question. You can mail us your question. We will forward to our professor. I hope
thank you.
He will reply. Now we are almost at the end of session. Thank you very much, Professor, for giving time for us and sharing your experience and work for us. This webinar was planned in a conversation and happening today. We are very grateful to you. Now, with the permission of our President, I would like to provide you a certificate of appreciation. I will just show.
Okay, yeah, thank you very much. Thanks for your attention and for the organization, of course. Thank you.
Thank you, Professor. I want to request you for your concluding words regarding this webinar. Then our president of this association will formally terminate the webinar. Now, I would like to request you for your concluding words regarding this webinar.
Yeah. Okay. So the concluding notes, I would say that first, and I think it was very clear from the presentation, Microgrids is not like having it's not a very closed system or defined thing. It's a philosophy of, let's say, produce, consume, store the energy. Let's say to have energy systems. And that's why we can apply these concepts here in the air, in the sea, in the space. So that's why we can really export this idea. And because what we have is finally a philosophy of doing things behind. Yeah. So that's, and the philosophy, it goes more on thinking locally. Think locally, think small, think on awareness of people, think to involve the people in the process. And finally, think that you, even if you are not connected to a microgrid, you should raise your awareness. Now, when you go to the kitchen and you see all these appliances, to raise your awareness of the use of energy, yeah, to raise your awareness every time that you do something. If tomorrow you have a party, you will think, okay, maybe I will carry some glasses from home, but you will not go to the supermarket to buy plastic glasses, right? So raise awareness and try to be really engaged on what you are doing in all the aspects that you can. So finally, also do it yourself. It's very important. This is the philosophy, no? Try to do it yourself, to recycle things, and to think on this direction, no? A little bit more. If we can achieve this kind of qualities in the persons, we will raise this in a global terms. That's why I was saying in this seminar that what I think with microgrids is like energy that goes from inside. When I say inside, I mean individuals, I mean small systems, out, no? That we can really build the whole energy system and even our own social, let's say, life, everything in this way. Yeah, so thanks a lot.
Thank you, Professor. Now it's a certificate of appreciation presented to you. It is, I want to read it. Electrical Engineers Welfare Association Nepal Certificate of Appreciation. This certificate is proudly presented to Professor Dr. Josep M. Guerrero for sharing his valuable knowledge as a guest speaker in the webinar on microgrids, energy from inside out, conducted by Electrical Engineers Welfare Association Nepal on July 10, 2020. We'll provide the certificate of participation to all the participants as soon as possible. Now, thank you, Professor. Now, I would like to request I want to thank Professor for his time and I would like to request our president for concluding words and to formally terminate the session. Thank you.
Thank you, Mr. Vinod, our secretary of the Electrical Engineers Association. I'd like to thank Professor Dr. Josep for your valuable time. We are very grateful to you. As well as I would like to thank all the participants. Those are participants from domestic as well as internationally. I like to thank all the committee members, those who are involved in the this webinar, as well as I would like to thanks all the other those who have cooperated and who are always with us for the cooperation. And coming days also will come with the webinar and seminar as well. So in this respect also, I would like to request or expect the cooperation from all the electrical engineers as well as from other part of the peoples. I would like to thanks all. And once again, I would like to thank Professor Joseph, and I'll announce the concluding of the webinar.
Thank you, sir. Thank you, everyone, for joining us. I will look forward hearing from in future too. Thank you, Professor.
Thank you.